Hello everyone, and welcome to today's webinar, How HashiCorp Vault Solves the Top 3 Cloud Security Challenges. Please feel free to type your questions during the webinar. We compile all questions and answers at the end of the webinar and send the results to everyone registered. This webinar is recorded, and the recording will be made available after post-processing, usually within 2 days. With that, let's go ahead and get started.
Awesome. Thank you so much, Amanda. And welcome everybody to our webinar on Vault and how we can use it to solve our top security challenges. Briefly, a little bit of context. My name is Armand Dadgar. You'll find me all around the internet as just @Armand. And I'm one of the co-founders and CTO of HashiCorp. For those of you who are new to HashiCorp or just learning about Vault, HashiCorp as a company is focused on sort of the entire application delivery process. And so the way we like to think about it is there's 3 distinct layers in terms of how we manage and deliver our applications. There's the provisioning challenge of providing the core underlying compute, whether that's public cloud, whether that's private cloud, or some mix. There's the security challenges of how do we provide access to secret material and secure our applications and data on that infrastructure. And at the highest level is the runtime of how do we run our applications, our services, and our appliances that we need for our infrastructure to work together. And so the way this comes together is we have 6 different open source tools. Many developers are familiar with or use Vagrant on a daily basis. That's where our journey starts. Then we have tools like Packer, Terraform, Vault, Nomad, and Consul. Today we're going to spend some time talking about Vault specifically. And then there's, for several of these products, there is an enterprise equivalent that's designed to be used for organizations and teams that are leveraging the open source version. So with that, let's talk about today's agenda. So we're going to start off by talking about what are the kind of top level use cases for Vault. Under what scenarios would you even consider Vault as a possible solution? Then I'll do a brief introduction to Vault, what Vault is and how it works. And then we're going to spend some time on the new features of Vault 0.7 and a few of them from Vault 0.65, which was the last major release. And then I'm going to do a quick demo and run through of what replication actually looks like with the service and how you'd leverage something like encryption as a service. So the top 3 use cases we see that drive people to adopting Vault is really secrets management, encryption as a service, and privileged access management. And so to talk briefly on each of them, secret management is the challenge of how do we distribute to our end machines and applications the secret material they need to function. So this could be things like database credentials, API tokens, such as your AWS access key and secret key. It can be TLS certificates to serve secure traffic. Anything that you might use to authorize or authenticate an application falls into this category. The next major use case is encryption as a service. So if we have data at rest, data at transit that we'd like to protect, how do we do that? This has challenges of key management. So if we have various encryption keys, how do we ensure that only a subset of people have access to those keys? How do we rotate them? How do we ensure that sort of the key life cycle is properly handled? And then in addition to just the keys is the cryptography itself, where Vault can help us by doing cryptographic offload. So instead of implementing cryptography in our end applications and making sure the producers and consumers all implement it the same way, we can offload the challenge to Vault and use its APIs to do sort of encryption for us as a service. And the last one is privileged access management. So if we have a central system that's storing our encryption keys, our database passwords, so on and so forth, how do human operators get access to it as well? So if I need to go in and perform some sort of maintenance operation against the database, I don't want to maintain that secret in a separate location and have one system for my apps and a separate system for my operators. I'd like to centrally manage all of that. And so the more human-oriented aspect of it is the privileged access management. So these are sort of the top challenges in the space. What I often find useful is to give sort of a brief primer on how should we think about the problem space itself. Like when we talk about secrets management, what are the challenges we're talking about? What this really starts with is defining what is a secret, right? And the way we think about it is it's anything that's used for authentication or authorization. So I can use a username and password to authenticate myself. I can use API tokens. TLS is being used to verify my identity. So these are very sensitive pieces of information. I'm sorry, these are very secret pieces of information. Sensitive, on the other hand, is anything that we'd like to hold confidential, but can't really be used directly for authentication or authorization. So for example, social security numbers, credit cards, emails, these are sensitive pieces of information, but they're not secret, right? And there's a delineation there because the volume we have of secret material, where we maybe have 1,000 or 10,000, or on the outside 100,000 pieces of secret material, we might easily have millions, tens of millions, or billions of pieces of sensitive information. So as we're talking about secret management, there is a number of important questions we have to be able to answer, right? How do our applications get these secrets? How do our humans, our operators, our DBAs get access to these secrets? How are these secrets updated? So if I change the database's password, for example, or my Amazon token expires, how do I revoke it? So in the case that an employee who had access to it leaves, or we just have a rotation policy, and we need to revoke it, or if something is compromised. When were secrets used? So as part of building a comprehensive audit trail, we want to know when secrets were actually used. And lastly, what do we do in the event of a compromise? So if we find that our database password has found its way to a forum somewhere, what do we do now? And so the state of the world that we generally see in answering these questions is what we kind of refer to as secret sprawl. Is that the keys, the secrets, the tokens, the certificates are sort of distributed all over the place. They live hard-coded in applications, they live in configuration files, they're in Chef and Puppet, they're in GitHub, they're in Dropbox, they're on wikis. So they're sort of all over the place. And so the challenge is there's this extreme decentralization of where this material actually lives. There's very limited visibility into where they live, how they're used, if they're updated, who has access to them. So there's sort of a challenge in terms of, from a security perspective, how we reason about that secret material. And then lastly, there's a very poorly defined break glass procedure. So in the event of a compromise, what we actually do, the procedure that we follow, is very hard to define because we really don't have much visibility or even central control because of this sort of secret sprawl problem. So this is where Vault comes in. This is where we look to sort of improve the state of the world. So Vault's goals from the onset were to be a single source for secrets. So sort of merging the kind of privilege access management of how our operators get access with our secret management of how our applications get access to give us that sort of centrality. And so we want to have programmatic access for our applications that are doing it in an automated way. And we want to be able to have a friendly access path for our operators who are doing it manually or on an as-needed basis. And for this to work, we really wanted to focus on practical security. And what we mean by that is there's always a trade-off between theoretical security, if I have access to the physical hardware and I can freeze the memory, can I pull out a key in transit, versus how difficult is this system to use or how expensive is it to operate. So our goal is to find a practical medium there. And lastly, when we say modern data center friendly, we really mean thinking about sort of cloud. So how do we do this in a pure software way that doesn't have dependencies on special hardware that we probably don't have access to in cloud environments. So the key features of Vault, at its most basic core is secure storage of secrets, right? And this is making sure that in transit and at rest, everything's encrypted. Then as we get sort of past the basic level storage, there's dynamic secrets, which we'll talk about. It's a mechanism for sort of generating credentials on the fly. There's a leasing, renewal, and revocation lifecycle, which allows us to have auditability and visibility and the key rolling and revocation story. Auditing is a critical part of this whole story, so we want to make sure we have that visibility, get away from that sort of low visibility state of the world. Rich ACLs, so we want to have very, very fine-grained access controls over who can do what. And lastly, multiple authentication methods. And this is important because we're going to have humans logging in with things like username and password versus applications which won't be logging in that way. So at the most basic level is how do we just make sure Vault can operate like a secure storage site, right? And so this promise starts by saying all data is encrypted in transit on the way from the client to Vault. as well as at rest. So when Vault is actually storing data on, on disk, everything is always encrypted. And everything is done with 256-bit AES in GCM mode. TLS 1.2 is mandated between Vault and its clients. And all of this is what is done in pure software. So there's no hardware requirement to make this work. And the goal here is to really encourage using sort of the state-of-the-art, the highest recommendation in terms of things like TLS and cipher modes. What does this actually look like? A very simplistic example is here we're just going to write a key to the path secret/foo, and we're just going to write the value bar is equal to bacon. The takeaway here is that Vault lets us store relatively arbitrary things. So bar is equal to bacon doesn't actually mean anything to Vault, but maybe it means something to our application in terms of it being a username or password. And it lays out its data in sort of a hierarchical file system. So here, secret / is a directory, and foo is sort of an entry within that directory. And then we can come around later and do a read against secret foo, and we're getting back
Okay. Yeah, it's not just you.
Hello, sorry about that. Looks like we had a temporary connectivity glitch. So like I was saying, every secret has a lease associated with it. And what this lets us do is automatically revoke at the end of a lease unless it's renewed. And so what this lets us do is a fewfold. One is it gives us certainty that the client is checking in every once in a while to renew its lease. So we have an audit trail of when a secret was accessed. In this case, if our refresh interval was 30 days, every 30 days, we can see the client is still making use of it. But we could also change that value and time box how long it's going to take clients to upgrade into the newest version. So we can say we know within 30 days, all of our clients are going to move into the newest version of the secret. And lastly, if something comes up, we believe the secret's compromised, something is an issue, this gives us a break glass procedure. So we can say we know our MySQL credential was leaked. We're now going to revoke that and use that as our break glass procedure. And so every client that has access to it, that credential gets revoked and they can no longer make use of it. So the question is how do we make this enforceable? How does Vault actually have the ability to revoke it? And this is really where the idea behind dynamic secrets comes in, is that if we actually gave the end client the true credential, if we gave out, let's say the root, MySQL password, there's no way to revoke it. Once the client knows it, we can't wipe its memory remotely. So what we'd like to be able to do is give it a sort of a different set of credentials that's specific to that client that can be revoked. And so what Vault does instead is it generates on demand a set of credentials that are limited access, the sort of following the principle of least privilege, will give you the least privilege capability into the system. And then that token, that sort of username and password becomes enforceable via replication. So every client has a unique credential that's generated on demand that is tracked. And if we decide to revoke it, we can delete their particular credential without affecting all of the clients at once, right? And what this lets us do is have an audit trail that can pinpoint a point of compromise, because there's only a single client, for example, that has that username and password. So under the hood, what that flow looks like is, suppose we have an operator, they request access to a database. That request goes to Vault. Vault verifies that the user has the right, privileges to actually be able to do this. And then Vault connects to the database and issues, a create command. So we create a dynamic new username and password that has just the appropriate permissions the user needs. This is all flowing through the audit brokers. So we get audit visibility that the user requested it, that we generated such and such credential. And then we provide this dynamic credential back to our user. So Vault sort of sits in the pre-auth flow. Then the user goes and connects to the database and uses that credential. So critically, the data isn't flowing through Vault, just sort of a pre-authentication flow. And the way we sort of support this is having this notion of pluggable backends within Vault. So this way, there's sort of that last mile integration glue where Vault needs to be able to understand the API of the particular system, but by making this very pluggable, it's easy for us to grow support over time. So today there's almost a dozen providers. It's growing all the time. Everything from cloud providers like AWS to RDBMS systems like MS SQL, MySQL, Postgres, message queues like Rabbit, so on and so forth. There's sort of a broad range of support for generating the sub-credentialing. And the key with all of this is really what we're trying to provide as we're centralizing our secret access is a way of providing authentication, authorization, and auditing in a uniform way across all of these different systems, right? And to that end, we have a few challenges. On the authorization side, we have two different real classes of entities that need to authenticate. There's machines, which need things like mutual TLS, tokens. We have a mechanism called AppRoll, which integrates with configuration management. And so these are automated workflows for authenticating machines and applications. And there's user-oriented methods, username and password, LDAP, GitHub, which are sort of more username, password, MFA, traditional authorization methods. Then the system exposes a single rich ACL system for doing authorization. Everything in the system is default deny. So access is provided as sort of a need-to-know basis by a whitelist. In our experience, this tends to be much, much more scalable as your organization grows, just because it's easier to reason about what you need access to versus what you don't need access to. And lastly, you get auditing across everything. So you have a request response auditing, and the system is designed to fail closed. So if it can't audit to any of the configured auditing backends, it will reject the client request, preferring to sort of reject an operation as opposed to do an operation that can't be audited, that has no visibility. So as you might imagine, a system like Vault, which is in this sort of pre-authorization request flow, is highly availability sensitive, right? If you need access to your database and Vault is down and you can't get your credential, that's a problem. So from the very get-go, the system was designed with an active standby model. So it could do leader election with console, elect a primary instance. If that primary fails, it will fail over to any number of its standbys, and so you can have a high level of availability of the service. Going one step further, 0.7, the latest release, adds multi-data center replication. So before you'd have one data center with an active instance and many standbys. Now you actually have many clusters, and those operate in a primary secondary model. So one cluster is sort of the source of truth, the authority of what the records should be, and then it mirrors to any number of secondaries so that you can lose entire data centers and Vault can continue to function. One of the interesting sort of challenges with Vault is if your data at rest is encrypted, it itself needs a decryption key. There's sort of the chicken and egg of how does Vault access its own data if it's encrypted. And what Vault forces is that this key must be provided online to the system. And the reason we do that is to avoid that key itself ending up in a config file that's handed to Vault, which itself is then in plain text managed, eventually ending up in something like GitHub where your root encryption key is there. And so that key that needs to be provided to the system, the master key, is in some sense the key to the kingdom, right? If you have that key, you can ultimately decrypt all of the data at rest. And so how do we protect against insider threat, right? Where we have an operator who has this key that decides they want to bypass the ACLs and access the data at rest. The way we do this is using what's known as sort of the two-man rule, or in our case, it's sort of an any person rule. But it's sort of, you can imagine the Red October scene of turning two keys to launch the nuke. Where how this actually works is There is the encryption key, which protects data at rest. There is the master key, which itself protects the encryption key. And then this master key gets split into n different pieces. So we have n different shares, t of which are required to recombine into that master key. So the default is that we'll generate 5 shares, 3 of which are required to recombine into the master key. So we need a quorum or a majority of our key holders to be present to do this. And so now what we're really distributing to our operators is this key share that on its own isn't particularly valuable. You need a majority of these keys to really be able to reconstruct access to the system. And so this lets us sort of avoid being concerned with a single malicious operator attacking data at rest. So sort of in brief summary, the challenge that Vault is looking to solve is the secret sprawl problem. And it really looks at 2 classes of threat, protecting against insider threats, largely through the ACL system and the secret sharing mechanism. And it protects us against external threats using a modern and sophisticated crypto system. So then briefly looking at encryption as a service, since this is a bit different than both privilege access and secret management, is there's a different set of challenges here, which is we have a large volume of sensitive data that needs to be protected. Unfortunately, cryptography is hard. It's very easy to get the subtle nuances wrong. And securely storing keys and managing their life cycle is also a challenge. So what Vault does is have a backend called Transit, where it allows us to name these encryption keys, foo, bar, baz, or name it after our application, maybe API. And then there's APIs that allow you to do operations using these named keys, such as encryption, decryption. And what this lets us do is prevent our applications from ever having access to the underlying encryption keys, so we don't have to worry about them exposing it. And by leveraging the APIs, we don't have to worry about the applications implementing encryption and decryption and these other operations correctly. So data can now be encrypted and the keys managed by Vault, but then the ultimate data that is generated, the sensitive data, can be decoupled from Vault and stored in our traditional databases or Hadoop or other mechanisms for storing potentially a very large number of records. And so this lets our applications outsource some of the heavy-duty challenges of secret management and encryption to Vault. What it looks like, sort of from a high-level perspective, is potentially we have a user that submits a request to our web servers with sensitive data. The application sends the plain text to Vault and says, please encrypt using, let's say, key web server. Vault audits that request, but then ultimately generates the ciphertext and returns that back to the web server. The web server is then free to store it in its database. The equivalent is now, so the decryption route is to fetch the ciphertext, flow that to Vault, ask it to do the decryption, and the web server receives the plain text. So in this way, Vault is only seeing sensitive data in transit. It's not actually storing it at rest. So Vault doesn't necessarily have to be able to scale to store billions of pieces of sensitive data. You can continue to use your existing scale-out storage but leverage Vault to do the encryption. Cool. So that was sort of a high-level intro into sort of the use cases and the architecture of Vault. Now I wanted to spend a little bit of time just highlighting some of the new features that have just landed. The biggest tentpole that came in 0.7, as I said, is multi-data center replication. Its model is one of a primary secondary, so one cluster is elected as sort of the source of truth that gets mirrored into all of the other ones. And so what this is really focusing on is the availability story, right? So it allows us to lose the primary data center or lose connectivity to it or lose any of our secondaries and have all of the other sites continue to function. One of the big challenges is, especially if you're using things like encrypt as a service, you might be doing thousands or tens of thousands of requests per second. So this replication model allows us to scale the request by load sharing across multiple clusters. The design of the system is fundamentally asynchronous. So the replication is not synchronous on write. This is because availability is a top priority for us. So if we're unable to replicate to a secondary because it's offline or there's a network connectivity challenge, we want the system to continue to function. Replication is transparent to the clients. So clients of Vault continue to just speak the same protocol unmodified. Their reads can be serviced locally by a primary or secondary. Any write they do gets forwarded to the primary, so the source of truth gets updated. And so at the core, the implementation uses a mechanism called write-ahead logging. So this is very familiar for folks in the database world, is transactions get written to this write-only append log, and we ship that log down to our secondary sites. If our 2 sites become too far out of sync, either because it's a brand new secondary or maybe a data center has been offline for hours or days. We may have to resort to reconciling the underlying data because there's too many logs to ship. And so the system makes use of a hash index to recover. And then we make use of an Aries recovery algorithm from sort of database land to be able to deal with things like power loss in the middle of transactions. So the general model is we have our primary and secondary clusters. Within each cluster, we have our active and standby instances, and they're sharing access to their storage backend, in this case, for example, console. And we're simply shipping our logs. So as new things are changing on the primary, we ship the log to all of our secondaries. If things get overly out of date, instead of the very lightweight log ship, they'll switch into a more active index reconcile to figure out exactly what keys have differed and use this process to sort of bring the secondary back up to speed so they can switch back to log shipping. The next big feature is an overhaul of the enterprise UI. So I'll show that briefly when I demonstrate replication. Specifically, some of the new changes around being able to do the encryption as a service from the UI, as well as management of replication itself. Some other cool tweaks that have come through is enhancing the ACL system. It's already an incredibly fine-grained system in terms of what you can control over, in terms of, can I create a key versus use the key versus delete the key? And now we can go even more fine-grained. So particularly, we can allow and disallow, so whitelist and blacklist, different parameters to the API endpoints of Vault. So, a brief example of that is with the transit backend that I mentioned, we can use that to create named keys. So we're using those keys to do encrypt and decrypt operations. So in this case, we might actually specify our policy to say the only types of keys you're allowed to create with the system. In this sense, we're going to restrict the allowed parameters to only AES typed keys. So Vault supports a number of other types of keys as well. And what we're going to deny is you being able to specify that the key can ever be exported from the system. So in the rare cases, you may want to support exporting a key if you need to be able to share that with third parties. But if you don't, why even allow an application to potentially export it? So here we can use the ACL system to enforce that a key doesn't get exported. Another option is forced wrapping. So one mode Vault supports is anytime we do a read against it, we can have Vault wrap the response. So instead of actually giving us the response directly, you can think about it putting the answer in sort of this one-time unwrapped shell. And so this lets us do things like have an audit trail to ensure that only the app that was supposed to expose it and look at what the database password is, for example, was the one that did it. Multiple people along the chain weren't exposed to the database password. And so largely this is a mode that when you do the read, you can issue to the database and it will do it for you, but now you can force it through the ACL system as well. So here's an example where maybe we're generating a certificate authority, and what we would like to say is at minimum, you have to wrap the certificate authority for 15 seconds, and at maximum 300 seconds. So we're going to time box the availability of this thing, and we're going to force you to make sure you're wrapping it, and there's only a single person who got exposed to it. The SSH Certificate Authority is a very new, neat extension. So the SSH backend lets Vault broker access to SSHing into machines. So instead of giving every developer access to SSH everywhere by distributing sort of the one PEM file or putting every developer's PEM on every machine, instead we give Vault the ability to SSH into these machines, and it brokers access. And it can do it in 3 different ways. One is dynamic generation of RSA keys, so it can just generate SSH keys on the fly. One is a one-time password-based mechanism, and the newest mode is a certificate authority. And so in this mode, what happens is a developer sends their SSH key to Vault and says, I'd like to SSH into this target machine. Vault verifies they have the permission to do that, and then it signs that key. So it signs it using a well-known public certificate authority key. The user then SSHs into that machine normally, but now using their signed key as opposed to the plain key. And then the dashed arc is representing that the server is doing a verification of that signature. So it's not actually communicating with Vault, it's just making sure the cryptographic signature checks out. And as long as that looks good, the user is allowed to SSH in. Now, what's nice about this approach is a few things, right? Is that the client only communicates with Vault pre-flight. Vault doesn't have to be in the SSH path. There's very minimal computational overhead of doing this. Vault's basically just doing a signature on top of the existing public key. There's no operating system specific integration, and it's a very simple and secure mechanism. It uses a lot of well-known and well-studied cryptographic primitives. batched encryption and decryption. So if we're making heavy use of the transit backend to do our cryptographic offload, it can often be more efficient to encrypt or decrypt many pieces of data at the same time as opposed to one request per. So this is a relatively new enhancement. We can basically batch many different inputs to be encrypted or decrypted. Improved auditing of limited use tokens. So we can generate access to the vault that says this user allowed to perform 1 operation or 5 operations. And it was sort of hard to audit, exactly how many operations were used before. Now this just shows up, in the audit log in a very obvious way. We can see the number of remaining uses for every request. And finally, a number of new backends were added. So the Okta backend has been added to allow us to do authentication against Okta, Radius similarly, and etcd version 3 has been added to support storing data at rest. So now I'm just going to briefly do a very, very quick demo of this. I'm going to start by just bringing up Vault 2 instances. So these 2 instances are just fresh, locally running instances. Nothing special about them. Then I'm going to fire up the web UI for both of them. So in tab 1, we have Vault 1, and in tab 2, we have Vault 2. So what I'm going to do is configure Vault 1 to be my primary instance. So I'm going to go to Replication. Currently, we're not enabling replication. I'm simply going to turn that on. Then I'm going to generate a secondary token. This is going to allow us to authenticate a secondary. So test, generate that. I'm going to copy this activation token. Okay, and then I'm going to come back over to our other instance of Vault that's running, currently its own independent instance. Go to Replication, enable this as a secondary, hit enable, and great. Vault 1 and Vault 2 are now connected to each other. This one is configured as a secondary. This one is configured as a primary. So now click in, we should see that they both have the same set of sort of backends mounted. We're going to add a new backend. So here we're just going to mount it on our primary, add our transit backend, a little description. So now if we go to our secondary and refresh, we should see, boom, the new backend has replicated and it's showed up. So over here, I'm going to create a new encryption key, call it foo. Just put in my name. Go ahead and encrypt that. So now I'm going to copy the ciphertext. So we put in plain text and got our ciphertext back. And now I'm going to actually just decrypt it on the secondary cluster. So I'm going to flip back over here. We'll go into our transit backend. We can see the encryption key foo has replicated. So go into that, go to decryption. I'm just going to paste in the ciphertext that Vault 1 encrypted, decrypt, and we can see we got the same plain text back. So in sort of zooming out, we can think about Vault 1 and Vault 2 as having been 2 different data centers. So we replicated from data center 1 to data center 2 that we are going to use Vault as an encryption as a service using the transit backend. We defined an encryption key named foo here. That got replicated across. And now we can see how an application could simply span multiple data centers using Vault to encrypt and decrypt data in a way that's going to ensure there's consistency and both sides can access it. That's all I had for my demo. I'm going to flip back and I'm going to hand it over to Derek now, who's going to tell us about how Atlassian is using Vault.
My name is Derek Chamorro. I am the Senior Security Architect at Atlassian, and I'm based out of Austin, Texas. And like Armand, you can find me pretty much everywhere as the red in the sky. That's my Twitter handle below. And I'm talking today about how we at Atlassian will manage secrets at scale. So for those of you who are unfamiliar with who we are, we make software development and collaboration tools for both on-premise and in the cloud. Here is a bit of our portfolio. We make Bitbucket, which is the Git solution for the enterprise, Confluence, which is team collaboration software, HipChat, which is instant messaging and chat for teams, and Jira, issue and project tracking for teams. And through some recent acquisitions, we acquired a company called StatusPage, which monitors your page status, as well as Trello for creating project boards. So where are we? We are over 1,700 employees now. And although we started in Sydney, we now have 7 offices across 3 other countries. We have many physical data centers, but we are rapidly increasing our cloud presence in AWS with services running in multiple regions. This is a quote from Roald Dahl's last book, but it also reminds us that we all use secrets, and in some ways we hide them in the most unlikely places as well. And with that being said, how did we get here? Meaning, how did we realize that we had a problem with secrets management? Well, we grew up, meaning we grew as a company. When you go from 10 employees to over 1,700 employees, the tools you develop should grow and scale as well. Our development teams grew considerably, and unfortunately, we realized that secrets management had become a bit of an oversight. When we looked into what our dev teams were using for secrets management, we found that we lacked a solution that the entire company could use. Some teams were using ad hoc solutions or homegrown things for secrets escrow and obfuscation, but others were not. Without a global solution, it also leaves one vulnerable to recovery procedures. Imagine having to update autonomous secret stores for multiple services, and that whole process being extremely time-consuming. It was at that point we realized that building a cloud-ready secrets management solution would become a requirement. Without a global solution, we couldn't enforce consistent policies. Concepts like key rolling, revocation, and auditing were not consistent with homegrown solutions developed internally. And at that point, we realized that we could do a lot better. So first we laid out some use cases for our solution. First and foremost, we needed a secure storage solution for existing keys. Second, we wanted the ability to create keys dynamically for encryption use. This would allow us to encrypt data from applications and then store the encrypted data securely. Third, we wanted to extend our existing PKI program to build out trusted service level CAs. This will allow our services to get X509 certificates dynamically based off of some kind of role. And finally, we wanted the ability to generate and store AWS access keys and temporary credentials. These credentials could be generated when needed and then revoked when no longer in use. So from our use cases, we started defining what our feature criteria would be. We wanted a solution that had fine-grained access control policies that our service teams could administer for their own specific use cases. We wanted the ability to bring your own key, and this is a requirement for our existing services, as well as a lot of services that still provision their own API keys. We needed the ability to rotate and roll keys to comply with our internal password rotation policies, and that's something that we share with our secrets management. And from that, the ability to audit their usage, so we could track things like expired key usage. Creating dynamic keys and wrapping them with a separate key was important as well, as Armand had mentioned, is bringing encryption as a service. And at the same time, also, we wanted a solution that, that could be accessed for services that lived either in our physical data centers or within a cloud environment. And we needed that solution to be highly available and resistant to service disruption. And HSM integration was important to us because we wanted to ensure that master keys were getting securely backed up. The last feature itself is important because it's related to our service mirroring model, which I'll show you in the next slide. So as a form of disaster recovery, we'll provision or mirror services across multiple regions as a way of recovering from a total regional collapse should it happen. We didn't think it could happen previously, but as you were aware, AWS suffered a massive S3 outage a few weeks ago. So this type of design is meant to mitigate that type of collapse. So we first provision a set of service clusters within US West 2 as an example here, along with their relevant API keys. And then what we do is we create the same service clusters in a separate region. And since these are the same services, we want them technically to share these exact same keys securely in some form of secure fashion. But unfortunately, up to this point, we couldn't find a solution that could do this for us. So we started the vendor selection process based off of our existing feature criteria, and it really came down to two potential vendors. First, we started with KMS, which is short for Key Management Service. And for those who are unfamiliar, it's an Amazon Web Services managed service for creating and controlling encryption keys. So taking it from our last feature criteria, we found that AWS did support per service policies in the form of IAM policies. And while they can be fine-grained, you really need to understand the full KMS object model to ensure that you are limiting specific key access. Unfortunately, you cannot bring your own key, so this wouldn't address existing keys in use or existing practices of being able to create your own API keys for your service. KMS does support rotation as well as auditing through CloudTrail, and it does support the ability to create dynamic keys and then wrap them with a customer master key per its customer master key attributes. But it does not address keys for services hosted in our physical data centers. KMS is only meant for AWS resources and will only create keys and handle and manage keys for you for AWS for its own resources. Although not needed, we want a solution. So it's also highly available because it's integrated within an HSM, and it does allow that additional layer for protection for its master keys. But the one thing where it did not support is, from that service mirroring model, was the ability to support key replication across multiple regions. KMS is backed by that HSM and does not allow key exportation outside of its respective region. And after spending weeks with their product teams, we realized this wasn't something they could do. So after KMS, we looked at Vault, in particular Vault Enterprise, to see how it matched our criteria. And off the bat, the access control policies in Vault are very fine-grained, mapping authentication backend and set of policies to a user or service. And in the next slide, I'll show you our design, which we use console for a storage backend. So this allows us to use our existing keys to be stored securely and still kind of stick to our model of services bringing in their own keys. Keys are leased and rolled as well as revoked, all of which are actions that are auditable. The transit backend, as seen in the demo, allows Vault to handle data in transit, mimicking that envelope encryption. And since we present Vault as internally reachable service, both our on-prem and cloud services are capable of reaching it. We've designed it to be highly available and have integrated Vault with our HM service, and that's a key feature of Vault Enterprise. And as Amon had demonstrated, keys are capable of being replicated to different Vault clusters. So in the next slide, I'll show you our design. There's a lot of stuff going on here, so I'll break it down for you in a bit and kind of show you the flow. So first we launch a Vault server and a console server in the same availability zone. A console agent sits on the Vault server that receives and forwards requests to its respective console cluster. Partitions are created on the Cloud HSM, and we use Cloud HSM as our HSM. It's an AWS service, and we just use it because it was something that was easily available for us. So we create partitions on Cloud HSM for the regions that serve our Vault clusters, and redundancy is built in within the HSM client binary as we point the client to both PKCS11 interfaces for each HSM instance. This interface is used for master key generation and escrow, as well as to securely auto-unseal Vault during a service restart. So if there is a failure with one HSM, since the key is technically written to both partitions, we always have a redundancy built in. As normal traffic flow, the normal flow is as follows. So our internal client at the top will make an API call through our shared core infrastructure. And this shared core infrastructure is connected to Amazon Web Services through the Amazon AWS Direct Connect connection. And these are redundant links. So if there's a failure on one link, we still have other links that connect to this per region. That API call is forwarded to an ELB instance within the respective region. And with the new replication feature, if a client is writing a secret, then it will replicate to all clusters. So in conclusion, by providing a single enterprise-wide solution, we avoid snowflake management models, as well as provide a solution that is available to both cloud and physical environments. This allows our development teams to focus on building amazing services and not worry on where to store keys, thus avoiding secret sprawl. With a centralized solution, we can build policies that match our security criteria. Tiered service level access, key rolling and rotation, as well as provide a full audit trail. And finally, as we expand to more regions, so will our platform, thanks to key features like Revocation. So that leaves us as a company feeling pretty darn good. And that's all I had. Thank you very much.
Thank you everyone for joining us for today's webinar, and thank you to Armand and Derek for presenting. As we said at the beginning, this webinar was recorded and we will make the recording available after processing. We will also send an email to everyone who registered for the webinar, the complete list of questions and answers after we summarize all that data. Thank you so much for joining and have a great day.